Okay. The next topic is a Lenz's law. So according to this, the magnitude of the induced EMF is directly proportional to rate of change of magnetic flux linked with the coil. So if E is the induced EMF, so d phi by dt, that will be rate of change of magnetic flux. Your phi is the flux, so rate of change of the flux is d phi by dt, and induced EMF, which we are denoting by E, so E will be directly proportional to d phi by dt. So let's say E is equals to k dot k into d phi by dt, where k will be a proportionality constant. Okay. So our formula of EMF comes as minus d phi by dt into, sorry, E is minus d phi by dt. So this is when there is one coil. If there are n number of coils, then EMF induced will be minus n d phi by dt. Okay. Next is polarity. Like what will be the current? Let's say you have taken a coil and there is a magnet. This magnet can move in both the directions, either forward or backwards. So we need to find what is the direction of current which is being generated in the coil. So according to it, this Lenz's law, the polarity of induced EMF is in such a way that it tends to produce a current which opposes the change in magnetic flux produced by it. Okay. So example I am giving. So let's say first we have taken a coil. Then this is north pole of magnet. This is south pole of magnet. Now this magnet we are going to bring closer to coil. So when this magnet is getting closer to coil, we know from north pole magnetic field lines will emerge. Okay, and these magnetic field lines, sorry, they will end at south pole. Okay. Now let's say when this magnet is brought closer to coil, then the number of electric field lines, sorry, number of magnetic field lines which are passing through coil will be increasing. So current through this coil will flow in such a way that it will try to decrease the magnetic field passing through the coil. So as you, let's say if coil is placed like here, and let's say your magnet was like this. Okay, here the number of magnetic field lines is increasing. So if current flows in anti-clockwise direction, so due to this current there will be a magnetic field which will be in opposite direction. So this magnetic field is trying to cancel out the increase in magnetic field. So in this case, current flowing will be anti-clockwise. Let's take another case. There is again a coil, and let's say this time we are taking north pole away. Okay. So when you are taking north pole away, now here we can see like from this side, magnetic field lines will be coming out. Okay. Once you are taking this south pole away, okay. So the number of okay, wait. Another case we are discussing. Uh, hmm. In the second case, the north pole is here, south pole is here. So we are taking this thing away. Okay, this magnet we are taking away. So we know again from north pole magnetic field lines will be coming out, but as this magnet is being carried away, the number of magnetic field lines uh, which are going inside, that will decrease. Now the current should be flowing in such a way that due to the current flowing in this loop, the magnetic field passing in this direction should increase. So here, if the current flows in clockwise direction, so the magnetic field will increase. Okay. So that's how we will be able to decide whether current is flowing in anti-clockwise direction or clockwise direction. Next is a Lenz's law is in accordance with conservation of energy.